The light aircraft carrier United States ship Independence survived the Pacific War only to face a much more absolute executioner. The vessel was reassigned as a target ship for Operation Crossroads at Bikini Atoll in 1946. It was one of the carriers placed into the test fleet, carrying instruments and equipment intended to show how naval combat architecture would react to the extreme physics of nuclear detonations. For test able, Independence was moored close enough to the 0 point to absorb the violence directly, but it was part of a wider target array rather than a single primary bullseye. The exterior hull warped violently and the flight deck buckled under the immense strain, but the carrier refused to sink. Surviving 2 atomic strikes proved the raw structural resilience of the ship, but it also created an irreversible operational problem. The carrier had been radioactively contaminated, especially after Baker, and the combined blast, fire, and contamination history meant it could never return to active fleet service. The vessel transitioned into a floating laboratory for radiological decontamination at Hunters Point in California. Over the next few years, the Navy used the damaged hulk to study the lingering effects of radiation on naval materials. Eventually, the utility of the ruined vessel expired. Because its post-test condition ruled out ordinary scrapping, the military establishment made an irreversible decision to dispose of the carrier at sea. In preparation for the final tow, the Navy used cleared interior engineering spaces for a secondary critical purpose. Radioactive materials associated with the Crossroads program were placed deep inside the hulk, including steel 55-gallon drums into which concrete had been poured as shielding. The record points to a controlled internal disposal load, not the simpler image of a flooded hull casually filled with loose waste. In January 1951, the final operational sequence commenced. The Navy towed the irradiated carrier away from the California coast and positioned it over deep, open water near the Farallon Islands. This was not a passive scuttling operation of open sea valves. The final disposal used explosive scuttling charges against an actual wartime hull that had already survived extraordinary punishment, while the documented record stopped short of proving a classified torpedo test or a measured yield experiment against armor. The charges detonated, the lower hull was breached, and the ocean rapidly flooded the remaining compartments. The carrier finally lost buoyancy and slipped completely beneath the surface on January 26, 1951. At that moment, the historical record narrowed sharply. Operational teams recorded the scuttling date and general surface disposal coordinates, establishing when the operation ended and roughly where the surface event occurred. Once water closed over the crippled flight deck, however, direct observation stopped. The final internal failure sequence, the ship's descent behavior, and its resting orientation on the seafloor remained unresolved, turning the condition of the contaminated carrier into a future forensic question. 2,600 feet of ocean depth off the coast of California creates an immediate and crushing environmental barrier. At this extreme depth, the ambient pressure dictates every parameter of human reach, instantly eliminating standard diving operations and enforcing a permanent standoff. However, the immense column of water is only the first layer of defense surrounding the site. When marine surveyors eventually locked down the exact geographic coordinates of the target, they achieved a critical positive knowledge gain. The resting place of the hull was no longer approximate. That location changed the rules of engagement because it placed the massive steel structure in the northern region of Monterey Bay National Marine Sanctuary, within a protected framework coordinated by NOAA partners across the greater Farallones and Monterey Bay region. The sanctuary placement triggered a jurisdictional control regime. Any disturbance, recovery, anchoring, or physical sampling would have to be justified under federal sanctuary rules. Engineers could not simply arrive at the coordinates and deploy heavy equipment. They would need to show regulators that their survey methods avoided disturbance and satisfied strict permit conditions. The friction was deliberate, prioritizing habitat preservation over investigative speed. Beyond the sanctuary laws, the specific historical payload sealed inside the ship introduces a second forensic limit. The potential radiological hazard generated by the cargo means that any breach, cutting operation, or recovery attempt would demand an extraordinary safety case. Safety protocols designed to protect both the marine ecosystem and the survey personnel push the mission toward non-intrusive inspection. Engineering teams cannot treat the wreck like a salvage target. They cannot cut into the hull, force open sealed hatches, or recover diagnostic equipment without a separate legal, environmental, and radiological justification. In standard salvage logic, verifying the identity and condition of a sunken vessel requires tactile interaction. Investigators typically clear away accumulated marine growth to read engraved hull numbers, or they extract a recognizable piece of machinery. Together, extreme depth, sanctuary law, and radiological boundaries strip away those tools, leaving only evidence that can be read without contact. Operating inside this denial regime required disciplined restraint. The challenge was no longer lift capacity, cable strength, or forced entry. It was controlled observation from outside the exterior steel. The lack of natural light and near-freezing temperatures compound the complexity of this non-intrusive mandate. Any remote instrument sent into this zone must withstand immense hydrostatic pressure while operating with surgical precision to avoid accidental collisions with the fragile structure. A single navigation error could result in a multi-ton vehicle crashing into the irradiated steel, instantly violating the primary objective of the mission. That protective regime creates the central forensic paradox. Traditional proof of identity depends on contact, yet this site denies contact. The question becomes how engineers can verify structure and identity using only remote evidence. Approaching a protected deep water structure demanded acoustic precision, standoff optics, and remote sensing. The initial phase relied on sound. In 2015, marine engineers deployed a specialized autonomous underwater vehicle known as Echo Ranger, programmed to fly calibrated grids high above the seabed. Operating without a surface tether, it could adjust its flight path, maintain safe altitude above wreckage, and carry a three-dimensional sonar payload across the entire site without physical contact. As the vehicle flew its pre-programmed track, it fired thousands of acoustic pulses down toward the seafloor. These sound waves struck the ocean bottom and the metallic anomaly, bouncing back to the acoustic receivers on the vehicle. By measuring the exact time it took for each individual pulse to return, the onboard computers constructed a highly detailed geometric model of the environment. This acoustic operation achieved a massive positive knowledge gain. The sonar data confirmed that the massive steel hull remained remarkably intact and sat perfectly upright. The unmistakable silhouette of a light aircraft carrier emerged from the digital point cloud, proving that the primary hull girder survived the violent descent through the water column. However, acoustic mapping still possessed inherent blind spots. The hardest limit sat at the interface where the lower steel meets the ocean floor. Any catastrophic damage inflicted on the lowest compartments may be hidden by the hull's contact with the seabed and by sediment, leaving the lower failure zone outside the reliable reach of that dataset. Acoustic returns provide exact dimensions and structural geometry, but forensic confirmation of identity and condition requires high-definition optics. To bridge this gap, a subsequent expedition launched the following year. In 2016, a dedicated deep ocean survey ship arrived at the coordinates to deploy a pair of remote-operated vehicles. Unlike the autonomous acoustic drone, these vehicles were tethered to the surface ship by miles of fiber optic cable. This umbilical allowed human pilots on the surface to control their movements in real time and stream live video feeds back to the control room. The objective was to conduct a strict standoff visual inspection of the upright hull. The pilots faced the immense challenge of maneuvering multi-ton vehicles in an environment dictated by zero natural light and shifting deep ocean currents. Deep water is often filled with suspended particulate matter. When powerful floodlights hit this particulate, it creates massive optical backscatter, blinding the high-definition cameras. To counter this, the pilots had to position their light booms at specific angles to penetrate the darkness without whiting out the video feeds. They had to fly the vehicles close enough to capture clear diagnostic images while holding a conservative standoff from the steel. Every lateral translation and vertical thruster movement was calculated to counter water flow, sudden shear, and the drag of the trailing tether. Together, autonomous sonar and strict standoff visual inspection formed the method fingerprint required inside the denial regime. The vehicles hovered outside the hull, recording visual data while the team topside maintained situational awareness. Acoustic outlines had already established the large geometry. Now the cameras had to test the granular exterior details, component by component. What specific forensic evidence still survived on the outer steel? As the high-definition cameras move across the immense vertical steel walls, the geometry of the target presents a stark visual trap. The crisp, manufactured lines of the original warship are entirely obscured by a heavy biological overprint. Decades of deep ocean isolation have allowed massive colonies of glass sponges to heavily colonize the exterior steel. These brilliant white, intricate structures blanket the hull plates, the protruding gun tubs, and the vertical bulkheads. They transform the rigid industrial shape of the carrier into an alien, heavily textured underwater forest. This vast biological incrustation acts as camouflage, forcing analysts to read the surviving evidence of the coherent main hull through dense marine cover. Once the eyes adjust to the immense sponge coverage, the overarching intactness of the primary structure becomes undeniable. At the bow, the cameras pick up the sharp, narrow, cruiser-derived form of the carrier class. Rising high above the main deck, the massive flight deck remains physically attached, but its plates are visibly warped and buckled from the earlier atomic test sequence. Even with that topside deformation, the visible bulkheads show no major separation and no complete break through the hull. Moving along the outer perimeter of the buckled flight deck, the visual survey zeroes in on the surviving defensive structures. Hanging over the steep sides of the vessel are the distinctive circular gun tubs. Inside one of these tubs, the rusted mechanical components of a 40mm anti-aircraft mount are clearly recognizable, still trained outward from the carrier's side. Just forward of this defensive position, the most critical piece of physical proof emerges from the darkness. Welded directly to the ship is a heavily reinforced pressure mast, universally nicknamed a Christmas tree by the military testing engineers. Built to measure blast overpressure during the atomic detonations, it remains a major visual authentication point because a test-specific structure survived both the nuclear trials and the plunge to the seafloor. That unified exterior geometry immediately triggers a severe proof ceiling. The remaining paradox is vertical. The visible upper shell stays coherent, while the damage that ended buoyancy must sit below the readable plates. No confirmed catastrophic openings from that sinking sequence are visible anywhere on the upper plates. The physical environment supplies the concealment mechanism. The immense weight of the unified hull drove the ship into the ocean floor, and undisturbed seabed mud now rises high against the lower exterior plates where the explosive damage would have to be read. Above the mudline, the massive exterior shell remains unbroken and offers no obvious scatter of torn steel. That absence does not prove every detached object stayed inside, but it makes the open elevator shafts and blast-warped hangar deck openings the next evidence zone. Inside this dark cavern lies a highly localized internal debris field. When a massive ship sinks intact, the immense internal volume becomes a violently chaotic environment. Every piece of equipment that is not permanently bolted down is violently thrown against the bulkheads during the long descent to the bottom. The most prominent piece of this internal puzzle is the recognizable remains of a Grumman F-6F Hellcat fighter aircraft. This machine was left aboard as part of the ship's post-war test history, and the dark flooded structure preserved enough of its form for remote cameras to read it as an aircraft rather than anonymous wreckage. The airframe still retains a striking forensic presence, but the details must be treated cautiously. Some components are visible and identifiable, while other areas are degraded, obscured, or buried in silt. The aircraft survives as a powerful archaeological marker, not as a perfectly intact museum specimen. The disposal cargo introduces the next evidentiary limit. Archival work identifies radioactive materials stowed in cleared engineering spaces, including concrete-filled 55-gallon steel drums placed inside the hulk before the final sinking. Remote imagery may show barrel-like objects and other debris within accessible openings, but the exact distribution and condition of the waste containers cannot be stated as if every drum has been mapped. The accessible imagery, therefore, has to be treated as evidence with limits. Documenting this internal evidence represents a massive positive knowledge gain, but the wreck also enforces a strict physical boundary. Open bays and accessible voids can offer localized views of aircraft remains, debris, and possible container-like objects, but the interior decks beneath them remain difficult to inspect. Severe structural collapse, sediment, darkness, and the need to avoid disturbance limit downward access. Remote vehicles could not push through debris or drive optical sensors blindly into hazardous wreckage to inspect deeper engineering spaces or lower hull compartments. Consequently, many lower interior decks, including areas where scuttling damage may have opened the hull, stay outside the confirmed visual record. The remote survey has mapped the intact exterior geometry and documented accessible internal clues up to the hard operational boundaries. With the structural evidence constrained by law, safety, and physics, what happens to a radiological site that can only be studied through disciplined restraint? The radioactive materials believed to remain deep inside the flooded structure project a long-term risk question over the surrounding seafloor. As deep ocean corrosion continues, sanctuary managers must protect the biological ecosystem while managing an uncertainty locked inside the wartime hull. The successful standoff survey addressed this challenge by turning the surrounding marine ecosystem into a practical sensor field. Carefully selected sponge samples from the wreck area and reference locations could be analyzed for radionuclides associated with the ship's atomic history. This environmental sampling produced an important positive knowledge gain. Laboratory analysis of the sponge samples did not show radiation levels significantly above ambient background, and the remote vehicle survey found no detectable radioactivity at the standoff distances used. The deep ocean water column also provides powerful shielding and dilution, but the conclusion must remain measured. The data support the safety of the surveyed surrounding environment at the time of sampling, while leaving the question of long-term change open. The environmental data therefore supports a cautious management posture. The engineering objective shifts away from recovery and toward monitoring the vessel's slow return to the deep ocean environment. That caution has a concrete engineering consequence. Rigging lift lines or attempting to remove degraded containers would create disturbance, uncertainty, and a separate risk profile that cannot be justified without a dedicated assessment. For now, monitoring means leaving the massive structure exactly where it rests. The non-contact survey effectively froze the condition of the target in time as an acoustic and visual baseline. Decades from now, advanced remote vehicles may return to the same coordinates, repeat the sonar grids, and sweep their lights across the same vertical bulkheads to measure corrosion, sediment burial, biological growth, and structural change over a prolonged timeline. The operation stands as a triumph of modern deep ocean engineering and disciplined operational control. However, the deep water site is still governed by time. The primary hull currently provides a formidable physical barrier, but wartime steel is not immortal. As the hull plating and internal structure corrode and collapse over the coming centuries, the site's central uncertainty will shift from identification to endurance. How long the wreck can continue containing its radioactive legacy.